Ceramics, cation-anion radius ratio. The stability of a material is due in part to the relative ratio of ionic radii, little r to big R, within the crystal structure. A structure is more stable if the number of oppositely charged nearest neighbors, or coordination number, is maximized. In other words, the cations and anions want to be touching the highest number of oppositely charged ions. When the anions, which are negatively charged, surrounding a cation, which are positively charged, are all in contact with that cation, the configuration is more stable. We can go ahead and look at this visually. In this figure, we can go and see all of our anions surrounding our positive cation right there. And taking a look, we notice that none of them are actually in contact with that central cation. This means that the structure is more unstable. Looking at the figure on this side, we do the same thing. We have all our anions negative surrounding our positive cation in the middle. And taking a look, this time we notice that all of them are in fact in contact with that central cation. This means that the structure is going to be more stable. Moving below, the coordination number, or Cn, the number of atoms that a central atom touches as its nearest neighbors. This is in 3D. And this coordination number increases with increasing little r to big R ratio. An easy way to think about this, more anions can touch the cation with a higher ratio. Once again, it's good to think of this visually. So we have our image right over here. We have our big R's over here, our little r's over there. And we can see this is going to be a lower coordination number, since the number of atoms right here and here touching a central atom right over here is only 2, 1 and 2. This means that our little r to big R ratio is going to be a smaller ratio. Moving to the image right over here, we once again have our big R's, and we have our little r right here in the center. And we see this is going to be a higher coordination number, since the number of atoms touching that central atom is greater. This time we have 3 as opposed to 2. Our little r to big R then is going to be a larger ratio. Example problem. What is the ionic radius ratio in crystal structure for nickel oxide, in which the radii for oxygen and nickel are 0.140 nanometers and 0.069 nanometers respectively? What is the atomic packing factor, or APF? And finally, find the density of our nickel oxide. First, we'll go ahead and write what's given. We know the radius of the oxygen is 0.140 nanometers, and since this oxygen is the anion, we'll call this big R. We also are given the radius of nickel, which is 0.069 nanometers, and since this one is the cation, it's going to be the little r. For part A then, to find the ratio, we need to do little r to big R. We can go ahead and plug in our values. 0.069 nanometers divided by 0.140 nanometers. Our units cancel out, leaving us with a unitless ratio of little r to big R being equal to 0.493. We can now continue on to the next page. Little r to big R continued. As we just discussed, the ionic radius ratio for nickel oxide is 0.493. Our next step for the example problem is to take a look at Table 1, which correlates the little r to big R ratio to the coordination number and the coordination geometry. Taking a look at Table 1, we can see that there are 3 columns. The first column corresponds to the coordination number. The second column is for the cation-anion radius ratio. And the final column is for the coordination geometry. Taking a look at our first row, we can see a coordination number of 2. This is for all ratios which are less than 0.155. Visually looking at the coordination geometry then, we can see that there are 2 atoms touching a central atom. Moving on to the next row, we can see a coordination number of 3. This is for ratios between 0.155 and 0.225. And visually we can take a look and see that there are 3 atoms touching that central atom. Next up is the coordination number of 4. This is for ratios between 0.225 and 0.414. Taking a look at visually, this is a little more tricky. We can see our first 3 atoms right there, and the fourth one is actually this one that we're looking through, and these all touch the central atom. Another good way to look at this would be the ball and stick figure. We can see we have these 1, 2, 3, and 4 atoms, and all of these touch the central atom, which are denoted with an X right here. Next up, the coordination number of 6. This is for ratios between 0.414 and 0.732. Numbering off again, we have 1, 2, 3, 4, the 5th atom, which we're looking through, and our 6th atom is actually tucked away on the back side. We can't see it, yet all of them touch this central atom. If we want to look at the ball and stick figure again, we can see the 6 atoms more clearly, and they all touch that central atom with the X. The final table value is for the coordination number of 8. This is for ratios between 0.372 all the way up to a 1.0 ratio. Looking at it, we have 1, 2, 3, our 4th one, 5th, 6th, 7th, and the 8th one, once again, is tucked behind, and they touch the central atom with the X. If we'd like to look at the ball and stick figure, we can draw our first 7, which are easy to see. We'll connect all those. Our last one is this 8th one back here. That's tucked away, so we'll draw the dotted lines. And all of these touch the central atom right here. Relating this back to our problem, we have the little r to big R ratio for the nickel oxide of 0.493. This value is greater than 0.414, yet less than 0.732. Knowing this, we can say the coordination number for nickel oxide is 6, since this corresponds to this table value right here. We know that ionic compounds with a coordination number of 6 have an FCC crystal structure. For ceramics then, this structure is also called a sodium chloride structure or a rock salt structure. This gives us the second part of question A, which we're looking for the crystal structure of the nickel oxide. Moving on to the next page, little r to big R continued. As we discussed, the crystal structure for nickel oxide is FCC. We can go ahead and take a look at that visually right over here. What we have inside the square is the FCC face, and everything outside is simply drawn to help visualize. What we want to do is go ahead and determine what little r, big R, and AR is in terms of this figure. And A is simply the length and the width of the face. Since A is the length, we can denote that this right here is A. And since it's the width, this means that this length is also A. Next up, we want to find the radius of the cation. This right here is going to be a cation, so that means that this length is little r. We want to find the length of the radius for an anion. This is an anion, meaning that this is going to be big R. What we want to go do next is put A in terms of R. So we have A is equal to big R plus little r plus little r plus big R. Visually we can see that because this is equal to big R, that's little r, that's big R. And that sum is equal to A. Reducing it then, we have A is equal to 2 big R plus 2 little r. We also want to determine the volume since we'll be using 3D. The volume then is equal to A multiplied by A multiplied by A. The way we got that is we have our face right here. That's A by A. And since it's a cube, we can go ahead and add depth. And that depth is going to be A. This then simplifies down to V is equal to A cubed. Next up, we want to determine how many atoms there are of the anion and cation in 3D. First up, we'll start with the anion. So that's the number of oxygen atoms. And this is equal to 4. The way we got that is we have 1/8 of an atom on each of the 8 corners. That sums to 1 whole atom. And we also have 1/2 of an atom on each of the 6 faces, which is equal to 3. We can do the same thing for the cation. So we want to determine the number of nickel inside this structure, and that's going to be equal to 4. We got this because there's 1/4 of an atom on each of the 12 edges. That equals 3. And there's 1 whole atom in the center of it. That equals 1. We can also draw this in 3D to help us better visualize. Our first interest is this corner right over here. That we can see has 1/8 of an atom on it. Next up, we'll look at the edge right there. That we can note has 1/4 of an atom. Next up, we'll look at the face right there. This is an atom cut in half, so we have 1/2 of an atom inside the cube. And we have right here the atom in the center, denoted with the X, and that's 1 whole atom. Next up, we can move to the governing equation, the atomic packing factor. The atomic packing factor is equal to the number of cations in the unit cell multiplied by the volume of a cation, which is a sphere. This is added to the number of anions in a unit cell multiplied by the volume of an anion, which is also a sphere. All this is divided by the volume of the unit cell, which is the cube we've been talking about. We can now go ahead and plug in our quantities. The atomic packing factor is equal to the number of cations, which is the nickel. We discussed that. We said it's 4. This is multiplied by the volume of a cation, which is a sphere. So that's 4/3 pi, and the radius of this is going to be little r, since it is the cation. This then is added to the number of anions. That's the oxygen, which we said is 4. Multiplied by the volume of an anion, that's 4/3 pi, and the radius at this time is going to be big R, since it is the anion. That's cubed. All this is divided by the volume of the unit cell, A cubed. We can go ahead and simplify that to be 4 multiplied by 4/3 pi. This is multiplied by the quantity of R cubed plus little r cubed. All of that is divided by 2 big R plus 2 little r cubed, since that's the expression for A. What we want to do is write out what's known now. So we know little r, that was given as 0.069 nanometers. And we also have big R, that's equal to 0.140 nanometers. What we need then is the atomic packing factor, and that actually is going to have no units, since it's a volume over a volume. Finally, we can go ahead and plug in our values. The atomic packing factor is equal to 4 times 4/3 pi. Multiply that by big R cubed, 0.140 cubed, plus little r cubed, 0.069 cubed. All of that is divided by 2 big R, 0.140, plus 2 little r, 0.069. That whole expression is cubed. The units for that, we have nanometers, which are cubed since it's a volume, divided by nanometers. Once again, it's cubed. This go ahead and canceled out, leaving us with no units as discussed. Finally then, our atomic packing factor is equal to 0.705. We'll now continue on to the next page. Little r to big R continued. The final part of the example problem wants us to find the density of nickel oxide, so we'll take a look at the general density equation. For this equation, density is equal to mass divided by volume. Now this is just the general equation. What we're going to want to do is break down these quantities for ceramic so we can see what we know. For mass then, we'll break it down to the atomic weight of the cations. The shorthand for this is summation AC. We'll want to know the atomic weight of the anions. The shorthand for this is summation AA. We want the number of formula units within a unit cell. That's going to be N prime. We'll discuss what that means in a minute. And we also need the conversion constant. That's NA. And we'll once again discuss that in a second. For volume, it's a little bit simpler. All we need is the volume of a unit cell. This we already discussed is V. Plugging it in then, we can have the governing equation for density. Density is equal to the number of formula units per unit within a unit cell multiplied by the atomic weight of the cations plus the atomic weight of the anions, all of that divided by the volume of the unit cell multiplied by the conversion constant. Now we want to find these quantities for nickel oxide. First up is the atomic weight of the cations. Nickel is the only cation in NiO, meaning that it's just the atomic weight of nickel. We can look that up and see it's 58.69 grams per mole. Next, we want to find the atomic weight of the anions. Oxygen is the only anion in nickel oxide. Leaves enough just oxygen, and that's equal to 16.00 grams per mole. You can look that quantity up. Next, we need to determine the number of formula units within a unit cell for nickel oxide. This number is equal to 4. The way we got that is by looking at the formula unit, NiO. We can see that in this formula unit, we have 1 nickel and 1 oxygen. As we discussed already, there are 4 atoms of each of these inside the unit cell. This means that our number of formula units within a unit cell is simply 4. This is a little confusing, so we'll try a second example problem real quick. This is going to be for nickel chloride. That's NiCl2. Breaking it down in the formula unit, we can see there's 1 nickel for every 2 chloride. If we apply the same principles of finding how many atoms there are in the unit cell, we can see there's 4 nickel and 8 chloride. This means that our number of formula units of the unit cell is equal to 4. The reason for this is 4 of these NiCl2s can fit within that many atoms inside the unit cell. 4 nickel and then 8 chloride since it's a 1 to 2. We can now move on to the conversion constant. This conversion constant is simply just Avogadro's number. This is equal to 6.022 times 10 to the 23rd. And that's formula units per mole. And the reason we want to do this is because we have the atomic weight and not the mass, so we need to figure out a way to convert from moles. Finally, we need the volume. As we discussed earlier, that's A cubed. And we know A is 2 big R plus 2 little r. Well, that's cubed. We're not able to plug in values. The density then is equal to the number of formula units within the unit cell, 4, multiplied by the atomic weight of the cation, 58.69 grams per mole. And we're going to add to that the atomic weight of the anion, 16.00 grams per mole. All this is divided by 2 big R, 0.140 times 10 to the negative 7. This 10 to the negative 7th comes from being centimeters now as opposed to nanometers, so we converted. We're going to add to that 2 little r, 0.069. Once again, 10 to the negative 7th, since we want it in centimeters as opposed to nanometers. This expression is cubed, since it's the volume, and we'll multiply it by the conversion constant, 6.022 times 10 to the 23rd. That's going to be 1 over moles. We have 1 over moles in the numerator and 1 over moles in the denominator, so that cancel out. This leaves us with grams per centimeter cubed for our units. Plugging that in, we can see our density is equal to 6.79 grams per centimeter cubed. Our answers for the example problem are thus A, our little r to big R ratio is equal to 0.493. Our crystal structure is an FCC rock salt structure. For part B, we need to find the atomic packing factor, and we can see that was equal to 0.705. And finally, part C, we needed the density, which we found to be 6.79 grams per centimeter cubed. This then are the answers to the example problem. We can also take a look at the real-world use of nickel oxide. Nickel oxide is used for pigments in ceramics, electronic ceramics, and it's also used as a reactant along with acid to form salts. It's then important to know the properties that we found in this example problem in order to ensure that the right quantities of nickel oxide is used in these applications.